Thanks. Yesterday, I told you about Qubit, a package that sits at the end of your scientific pipeline. You design your simulation, you run your simulation, you want to know what's inside, you want to do some post-processing, you want to publish your paper, make plots. Today, I'm going to tell you about a package that sits at the opposite end. That is the preparation step. Jhuki is a Python package to help you run and design. Okay.
If you can continue, it's fine. Silly me. Share screen. Jhuki. Share. We're all set.
It's only first page. Yeah, it's only that. Okay. Yeah, so Jhuki is a Python package to help you prepare and run your simulations for Einstein Toolkit and cactus-based nodes. So what's the motivation? Let's make a thought experiment. Let's run this thought experiment. You want to run a quasi-circular binary black hole simulation. This is a very reasonable task to do with the Einstein Toolkit. So let's see what are the steps for this. Well, you take a parameter file. Let's see QC0. This is QC0 parameter file. You're not supposed to be able to read this. It's just a mess. And here now you have. Let's suppose that you want to change the orbital parameters of your black hole. Say you want to add spin. But then you quickly realize that if you want to change the black hole parameters, well, you probably have to change the Greek structure because you want to ensure like enough resolution. Well, if you change the Greek structure, probably you want to change some other parameters to ensure stability conditions. And if you change those parameters, all the fundamental frequencies in your simulation, say output and new output, those will probably change as well. And not only you have to change the Greek structure, you probably are going to change the initial guesses for your horizon finders. And you probably, if you want to have a quasi-circular inspire, you also have to change the other black hole parameters to ensure that your inspire doesn't have eccentricity. So as you see, a very, very small change leads to a huge change in the parameter file. And this is not easy. So I think that preparing parameter files is hard and error prone. And I have at least this set of reasons for why this is the case. First, there's all this complex interplay between parameters. And if you make a very small change, this can cascade to a significant change throughout the entire parameter file. And not all the parameters are created equal. There's some parameters that clearly control physics, black hole mass. There's some parameters that clearly control infrastructure. And there's other parameters that no one knows what they do. They're copied over from some ancient par file that are just there. And all of this makes preparing parameter file extremely easy to make mistakes, but extremely difficult if you're a beginner. You run your tutorial, you're given the parameter file. If you want to do something else, what's the next step? I don't know. That's a difficult question. So this is my take on parameter file. I think they're hard. So my solution is to make what the Einstein Toolkit maintainers don't want to make, that is have a full programming language to control parameter files. That is, I want to use Jhuki or Python to take care of the low-level details, similar speed as Qubit, but for the preparation of parameter files, so that I can expose the physics and leave everything else taken care of. So you can just set the parameter file, the parameters that control, again, the science, and you ignore all the other details. So let me tell you a little bit more about this. So SimFactory can run Python files. If you provide an RPAR file, what SimFactory does is it first executes the parameter file as a script, and then it takes the output and run that output as a Einstein Toolkit or Cactus simulation file. So what I did is I packaged in a library, Jhuki, a bunch of high-level interfaces to make to leverage this feature of running Python file to produce par files in order to, again, set most of those low-level parameter files, most low-level parameters. So let me show what I mean. So in this type of approach, you initially have some form of a Python Jhuki code, and then you have a sort of a template parameter file, similar to what you will write if you didn't use infrastructure at all. But this template has some gaps. Say, instead of writing all the code for binary black holes, you just leave you leave it blank, and you have a variable that starts with Bozzola and Jhuki is going to fill that section with all the relevant code. And then you write a parameter file and you run in the same way you would run any Einstein Toolkit simulation if you use the same factory. So let me give you an example. If you want to run a quasi-sequence file, you can just look at the physics. So if you can import the module, two-function module in Jhuki, you set your physical parameters, you run the function, and this also uses NumPy PN to ensure that this is a quasi-sequence file and whatever physical parameters you provide. And this two-puncture variable contains all the code that you have to set related to two-puncture for multiple forms to ensure that you have a quasi-sequence file. So what you can do is you can put your two-puncture variable in your template file, and you don't have to worry about setting the parameters for two punctures. And here, what I'm also showing is that this makes it very easy running parameter studies without writing multiple parameter files. What we can do is you can make parameter adjustable via command line, as I'm doing here, this parb, which is a separation. You can say, okay, I want to be able to control this via command line. So let's say that this is a sim factory object. Then I prepare my quasi-sequence file. This is, every time is automatically computed. So all the code for the parameter files is automatically computed every time you submit a new simulation. And then here you just run your single RPAR file in which you provide your the parameter that you want to study. So you can run any type of quasi-sequence file without rewriting
2 minutes.
Just reuse the same and let Jhuki Python compute everything that has to be computed. So to give another example of interfaces, if you want to have more control over the grids, here I'm showing how this is implemented in Jhuki at the moment. You define refinement centers that take refinement radii, and then you can combine multiple refinement centers in a grid object. And you can act upon this grid object in a meaningful way. For example, when you have a lot of refinement levels, there is stability conditions that you have to take care of. And you can ensure, for example, that the maximum time step on your grid is not too big that you run into these type of numerical instabilities. So this to me was a big point of pain, and having this programmatically set up is really convenient. And the number of errors I make is much, much smaller. So what is the state of the Jhuki at the moment? Well,
1 minute, please conclude.
This is a code I developed to solve a problem, and to solve a problem that I have. So the implementation is really bare bone at the moment. It's just trying to solve this problem. And I would say it's more of a proof of concept. It solves my problem, but for example, there is no support for multiple forests. However, I think it's a good starting point. I think it's a good idea to pursue this type of approach to
30 seconds, please conclude.
Errors and to make to make the code more beginner friendly, or the Einstein Toolkit more beginner friendly. So in conclusion, I believe that Jhuki reduces making errors with when preparing parameter files, also because there's some internal consistency checks. Significantly simplifies running parameter studies because you can just write one single RPAR file and just use it multiple times. And finally, it exposes the physics so that I can give new students an RPAR file that clearly shows which parameters should be touched and which should not be touched. And they can more easily start running simulations on their own. So I think that's it. Yes.
Yeah, questions?
So basically, you're going to have a module for each type of project you want to run with this approach.
At the end, you have like a module per each form, kind of.
Yeah.
Yes.
So I guess one of the next things you need for, say, beginner users would be a TOV star version.
Yes. So I have a TOV Python solver.
Okay.
Yes. Well, it's not in Jhuki, but I have it. Okay. At the moment, I'm running binary star, but the idea is yes. If I want to set the grid, I will solve with Python a TOV solution, and I'll bootstrap the grid from there. Yes.
And this could potentially be a tutorial for how to create the power file for situations that Jhuki doesn't cover. Because you could look at what you put in Jhuki, and you could look at the output.
Yes. But again, as you say, it's really dependent upon the thorns that you want to put in. You have to recreate all the abstraction in Jhuki. And there is some opinions that I'm like assumptions that I'm putting there.
Sure. But in principle, they have to have that. Yeah. They could fall into umbrellas like DOV or finding neutron star or finding a black hole. They could fall into this big module that.
Yes. Yeah. So for example, for binary black holes, like the function prepares, you can prepare the quasi-circular spiral that sets all the two-puncture radian base. Then you can attach the grid onto this two-puncture object. Then you can attach the apparent horizon. So everything reads from each other. So you can ensure that all the different parameters are set consistently without having to do it manually.